we're going to look at some other types of numbers. And one of the things that happens in mathematics is we invent new numbers when we need to do different things. And so we started out with natural numbers, which are our counting numbers. And we've invented integers, which have the idea of position relative to 0. Or as we would say, they're negative. They have negative numbers. And the next numbers we're going to look at, get a Q, are called rational numbers. And what we say are rational numbers are built out of a division where and it's the set of all numbers such that A and B are integers and B cannot be 0. And so we come up with the idea of a fraction. And so the upstairs is called the numerator, and the downstairs is called the denominator. Okay, so the numerator is A, and the denominator is B. And rational numbers represent fractional portions. And the Greeks first came about this by dividing things, right? And we all tend to think of it as like the pi concept. Right? I've divided this into 4, and I have one of them, and that's 1 out of 4. Now, what we want to do with rational numbers is we want to reduce them. We want to get them into a unique form or a simplified form. And so we have these numbers that are made by a division. A over B is a division, and it's also a fraction. It can represent both, and I'm hoping we can see that the idea of dividing things into parts and dividing groupings of numbers will have a similar pattern, and that pattern will have meaning depending on how we use it, that takes on the same context. Now, if I take any rational number and I'm going to multiply it by the number 1, I get the same rational number back. But I can multiply it by a very special version of the number 1. I can do the number 1 such that it's divided by one number, or multiplied by one number over itself, right? 3 over 3 is 1, 4 over 4 is 1, and so on and so on. So anything divided by itself is 1. So, and if I multiply across the top of my rational number, I get this new rational number, but it's equal to the one I started with. And we call this equivalent fractions. And let's an example. If I take 1/2 and I multiply the top and the bottom by 3, I get 3/6. And I can say 1/2 is equivalent to 3/6. But we like to write it in what we're going to call its reduced form. And so what we do to get into reduced form is we find the greatest common divisor, so of the numerator and denominator. So let's say I have 130 and 455. If I want to find the greatest common divisor, I'll do my factor trees. So 130 is 2 and 65, which is 5 and 13, so 2, 5, and 13. 455, well, I know there's a 5 in there, so that's 5 times 91, which is 7 and 13. And so the common numbers are what? 13 and 5? Right? Or 65. And so there's 65 goes into both of these numbers. In fact, I can write this as 2 times 65 over, let's see what we have here, 7 times 65. And because these both have 65 in them, that's the same as multiplying by 1. That can cancel. Or I get 2/7. And so the greatest common divisor helps me reduce fractions. Now, fractions talk about parts of things. And one of the things that we can talk about is we can mix fractions. So I have 3 and 4/5. Now notice how I say that vocally. I say 3 and 4/5. That's the same as 3 plus 4/5. And so I could write this as an equivalent fraction by talking about 3. Well, I want to get 3 to have the same denominator as this number. So I need it to have 5. So I'll take 3 over 1 times 5 over 5 plus 4/5. And I'll get 15/5 plus 4/5. Now because they're broken into the same number of parts, I can add up my parts and say 19/5. And so 3 and 4/5 is equal to 19/5. But there's a quicker way to do all of this. The way this number is written out, I can multiply the 5 times the 3 and then add the 4. So 5 times 3 is 15 plus 4, 19, and I've kept it all over 5. And so I can rotate my way around clockwise, multiply, add, and I turn the mixed number into what we're going to call, so this is called a mixed number, because it has a fraction and a whole number, into an improper fraction, because its top is bigger than its bottom. And so to convert an improper fraction to a proper fraction, or to convert a mixed number into an improper fraction, we multiply the bottom by the whole number and add the numerator. And then we put that total over top of the original denominator. Well, we can also go the other way around. We can take a improper fraction and we can take it, we can do the division that it says and pull out the remainder. So what we can say is, divide the numerator by the denominator. My dog is snoring. So sorry. By the denominator. And the quotient will be the whole number. And then the remainder we place over the denominator. Let's do an example of this. So if I take 48/5 and I want to turn it into a mixed number, well, 5 goes into 48 9 times. 9 goes into 48. 9 times 5 is 45 with a remainder of 3. Take the remainder and I put it over 5. And so 9 3/5 is the same as 48/5. Well, we can also turn a fraction into a decimal. Because this is the same as division, this is the same as saying 5 divided by 8. If I use my place value algorithm for division, 8 goes into 50 6 times. Gives me 48. Goes into 20 twice. 5. And so 5/8 is equal to 0.625. But sometimes we get an answer. See if I can keep doing this here. 3370 that repeats. And notice it's repeating 2 digits, 0.63 over and over again. And the repeating digits, I will put a line over top of to say they repeat. But we can always use the division as a way of making a decimal. Just there are certain fractions that we can't represent it as a decimal without repetition. Right? A third is a classic example of that, right? We get 0.33333, and it's whoops. And it repeats the 3's forever. It doesn't mean that there isn't an exact representation of it. It just means it doesn't convert to decimal form. We can also take a repeating decimal, and we can take any decimal and turn it into a fraction, and we can take any repeating decimal and turn it into a fraction. So let's first take a non-repeating decimal. Take 0.49, and we want it to be a fraction. Well, this is the tenths place, and this is the hundredths place. And so the hundredths place is telling me that I have 49 things out of 100. And so my next step would be to reduce. But this is already reduced. I could look at 0.048. So that's the tenths place. That's the hundredths place. That's the thousandths place. So I have 1,000 in the denominator and 48 in the numerator. But both of these numbers are divisible by 8. I have 6 over 125. Right? They're both factorable by 8. But what happens if we have a repeating decimal? So let's take 0.6 repeating. And so what we're going to do is we're going to turn this into a little algebra experiment. We'll say n equals this. Now, if I multiply this by 10, now this is repeating. So what I want to do is I want to multiply it so I get to the other end of my first repetition. And so I'm going to multiply it by 10. And it continues to repeat on forever. But now, if I subtract these from each other, the repeating parts are going to subtract away. Right? 10n minus n is 9n. And the repeating parts subtract away, I'm left with 6. And now I can do my division. 6 over 9. Both are divisible by 3, so 2/3. And so we can use the repetition as a way of getting rid, or of converting, repeating decimals back into their fractions. Let's do another one of those. So let's look at 0.63 repeating. And so this is going to continually repeat. So I'm going to let that be n. I'm going to go 1, 2 is what I need, so I have to multiply by 100. So I'll do it up above. 100n equals 63.63 repeating. And so I'll subtract these. 99n equals 63. And so now I'll divide, and I'll get 63 over 99. Well, both of these are divisible by 9, and I get 7 over 11. Now I should note that was the one we used up above in the previous example. And so we have this way of going back and forth between decimal representation and rational number decimal representation. Now, I've already used the fact in showing examples here, but multiplying rational numbers is actually one of the easier things to do with them. And we'll write it in this form. We multiply the upstairs. Whoops, that should be a D downstairs. We multiply the upstairs, and then we multiply the downstairs. And so they blend in an upstairs to upstairs fashion. So, for example, negative 2/3 times negative 9/4, and negative times a negative is going to be positive, and that's going to give me 2 times 9 over 3 times 4. But notice, those will cancel, and those will cancel. Alright, that gives me a 2 down there, and a 3 up there, or I get 3 halves. And I could write this as a mixed number, as 1 and 1/2. I personally prefer improper fractions, because that's how I use them, but we tend to speak this way. Now, if I divide fractions, well, here's where the idea of the reciprocal comes back in. I can turn this into a multiplication. Remember, a division is equal to a multiplication times a reciprocal. Well, here I'm going to take this division and I'm going to multiply by the reciprocal. But what is the reciprocal of a fraction? Well, I take the upstairs and downstairs and I switch them. So if I could have negative 3/5 divided by 7/11, I would write that as negative 3/5 times 11/7. Now I have a negative times a positive, so this is going to be a negative 33/35. I really do like multiplying and dividing fractions. It goes a little bit easier. But when we go to add and subtract them, we need to make sure that the denominators are the same. And so to do that, we use what's called the least common denominator. And so what we want to do is we want to find the denominator, LCD, the least common denominator, which is the LCM. It's made out of the least common multiple of the denominators. So if I have 3/4 plus 1/6, the only way they'll add is if their denominators are the same. I'm counting up how many parts I have, and I need them to be in the same number of parts. So I need to find the LCM of 4 and 6. And so I take the factor tree of 4, which is 2 squared, and the factor tree of 6, which is 2 and 3. So I take the greatest one of the 2's and I multiply it, right? Grab every factor. So 4 times 3 is 12. And so the least common denominator of these are 12. Now I can't change the value of what I have here, so I have to multiply these things by 1 in a way that I make their denominators 12. So 3 times 4 is 12, and that's 1. So I don't change the value of this term. And 2 times 6 is 12. So I multiply it by 1, so I don't change the value of this term. And so I get 9/12 plus 2/12, or 11/12. And so the least common multiple that we found will help us find least common denominators, because we want the denominators to be the same to add them. Now, we can always redivide things. So if I have two numbers, I can always put a number in the middle of them. And what we do that by is finding the halfway point. And so when we find the halfway point, let's say I wanted to find the number halfway between 0 and 1. Well, I add 0 and 1, and I divide by 2, and that gives me 1/2. Now let's say I wanted to find the number between 1 and 1/2. I want to find the halfway point in here. And so I add these two numbers. So I add 1 plus 1/2, which is equal to 2 halves plus 1/2. So I get 3 halves. And now I want to divide this by 2. And so if I divide it by 2, 3 halves divided by 2 is the same as 3 halves times 1/2, or 3/4. And so 3/4 is the halfway point. And I can constantly make halfway points. So I can say that 1/2 is less than 3/4, which is less than 1. And I could put another halfway point in here, and I could continue doing that. Alright, so, and these are rational numbers, which again extend what we can do. We've had counting numbers and we've had rational numbers. We'll only have one more set of numbers to add, and then we're going to have to pull all of our rules together. And we'll do that really in the next module.